Compound X is carbon, hydrogen, oxygen. There's the carbon and hydrogen percentages. Well, of course, the rest is oxygen. So the oxygen is going to be 100 minus 53.3 minus 11.1, which is 35.6. Turn that to grams, turn those to moles, turn that to a ratio. So the empirical formula, C2H5O. Mass of that empirical formula, 45. Why do we care about the mass? Because when we look at the mass spectrum, we see these various peaks here. Nice simplified version, so we're going to assume each of these peaks are important. First thing to notice is we got 90 there. This is the highest peak, and 90 is 2 times 45. So we can assume that this is the molecular ion, and therefore that the molecular formula is 2 times the empirical formula, because the molecular mass is 2 times the empirical mass. So the molecular formula C4H10O2. As soon as you see a molecular formula, figure out the unsaturation. 4 carbons requires 10 hydrogens. Oxygen doesn't count at all to that. So therefore we can say it's saturated. So no rings, no double bonds, no messing around. Now let's see if we can assign the rest of these peaks. We got peak of 15, which of course is CH3+, a nice methyl group. And when we take 15 away from 90, we get 75. So presumably this is the fragment that has lost a methyl group. 73 is 17 away from 90, and 17 is a nice OH. So presumably, therefore, this 73 peak is after we've lost an OH. 45, well, 45 is half of 90. So we'll assume, based on really nothing else, that that's half the molecule. So quite a bit of information. We got the molecular formula. We know it's saturated. We know it has a methyl group, and we know it has an OH. So here's where we are. Here's the molecular formula. We know there's an OH, we know there's a methyl. Let's look at the infrared. And the first thing is there's that gorgeous, beautiful OH stretch there. And the other thing we can get from the infrared is what's not there. There is no big CO dipping peak down here. Okay. Low res proton NMR has 3 peaks, so that tells us that there are 3 different hydrogen environments. We already know about 2 of those. We know we got an OH in there, so that's one type of hydrogen environment, and we know we got a methyl group, so that's another type of hydrogen environment. So the third type will have to be a CH or a CH2. When X is warmed with excess acidified potassium dichromate, there's a color change. Now, potassium dichromate oxidizes things. Okay, well, we know we got an alcohol, and you can oxidize primary or secondary alcohol. So this tells us that we don't have a tertiary alcohol here. However, after we've done this oxidation, then the product doesn't react with aqueous sodium carbonate. Well, if primary alcohol gets oxidized by potassium dichromate down to an acid, so therefore it is not an acid, not a primary alcohol. So what we have here is a secondary alcohol. Use all the data to find the structure of compound X. Explain what information we found from each piece of data. Well, we know we got methyl group, that's methyl groups. We know we got 2 OHs, there's 2 OHs. We know they have to be secondary, and we know we got 4 carbons. So 1, 2, 3, 4 carbons. You got to put the 2 OHs on there as secondary. So really, we could put them on there and there, or there and there. However, if I put them on the same carbon, now it would have 1, 2, 3, 4 types of hydrogen environment. We've only got 3 types of hydrogen environment as shown: the methyl hydrogens, the OH hydrogens, and then each of these hydrogens identical to this one. Again, kind of fun. Another X. So first of all, we've got the percentages of carbon and hydrogen. We're also told it has oxygen, so oxygen must be 53.33. Turn into grams, turn into moles, turn into a ratio. So the empirical formula, CH2O. Mass of that is 30. Here's our mass spectrum. And we see, without further ado, that the highest peak is 90. Okay, nothing past 90. So now we're going to assume that's the molecular ion, and that is 3 times 30. So thus the molecular formula has to be 3 of these. So C3H6O3. Again, let's look at unsaturation. The oxygens don't contribute. 3 carbons would usually like 8 hydrogens. We've only got 6. So 1 level, 1 degree of unsaturation. Got a methyl group there because there's that 15. Again, the thing that A-level thinks is so important. We got a 17, which as described previously is probably an OH. We got a methyl, we got an OH. Got 45 up here. See OOH possibly, okay. It's one of the few things that is a definite 45 there, 32 plus 12 plus 1. So we've got methyl, we got OH, we possibly got a acid group, and we got 1 level of unsaturation. It would of course go with the acid group. Moving on to the infrared, remember we're pretty happy that there's an OH and we're pretty happy that there's an alcohol in there. Both of these pretty diagnostically recognized on an infrared. First of all, look at the OH region. You've got the start of a beautiful broad hump there that then gets overlapped by a big mess here. The beautiful broad hump starting is an alcohol OH, messed up by the nastiness is a typical carboxylic acid OH. Then continuing on with the oxygen theme, we've got a beautiful carbonyl stretch there, the C double bond O, that's as we would expect for an acid, a little bit ugly as one expects for an acid. And then finally, you could argue that this is the CO bond here to go with the alcohol. So infrared pretty much adds great emphasis to the fact we've got OH and we've got carboxylic acid. Now that takes care of all 3 oxygens. It also takes care of the degree of unsaturation. Now let's look at the proton NMR. There's the chart for proton NMR. First obvious one all the way downfield there. There's our acid group. Now we got 6 hydrogens in the whole molecule. 3, 1, 1, 1 is 6. So in other words, this is 1 proton for sure there. This is 3 hydrogens for sure there. So there's our methyl group. And then the other 2 hydrogens, what we're seeing here is that they are different environments. Okay, so let's see if we can put everything together. We know we've got a methyl group. We know we have an acid group. We know we have 1 carbon that's going to be in the middle of those. And then the only question is what else is in there? Well, we've got an alcohol group which has to go on carbon 2, and we have this other one here. So this H here is presumably this proton, and this H here, the OH for the alcohol, is presumably this one. So this would be my analysis for X, the acid from the mass spec and the infrared and the proton NMR, the OH from the mass spec and the infrared, the CH3 from the mass spec and the proton NMR, and then the fact that this H and this H are different from the proton NMR. So same question on the exam, but switching to carbon NMR and switching molecules. So we got to draw the spectrum expected from ethyl ethanoate. We've already got carbon A there. Let's make it prettier. So we've got to have a pink carbon for the methyl group there, a red carbon for the ester carbon, and then a blue carbon for the start of what was the alcohol going into the ester. Here's our chart. So what we got there? Well, the first thing we have is we've got a R to a C double bond O to a C. So the R, of course, is this bit here, and this methyl group would be right there. So we're expecting the pink one to be somewhere between 20 and 50. Let's throw it in around there, shall we? Next carbon we've got is, of course, the ester, that one right there in red. Ester is going to be all the way downfield between 160 and 185. So let's draw it there, kind of all the way up at 185 just for fun. So the last one we got to do is the blue. Now, what do we know about the blue? It is a carbon that is attached to an oxygen and another carbon. So that's it right there, somewhere between 50 and 90. So popping in right there, sort of 80-ish, give or take. Okay. Fairly straightforward by just using the little chart. Student said valuable information about the nature of sample can be obtained from peak heights in carbon-13 and proton. Is the student correct? No. Correct for the proton NMR, as we've applied so far. Generally incorrect for the carbon-13. Now, when I went through the NMR worksheet separately from this, I pointed out that there are some spectra where you can look at where you've got two types of carbon and you've got two of one type and one of another type, that the peak heights are bigger, but it's really not something to rely on. And the reason is that for proton, 99% of the hydrogens in there are 1H, but for carbon-13 spectra, only 1% of the carbon atoms are carbon-13. So you just aren't enough in there to give you the really good data. So first of all, explain briefly how peaks in NMR spectra and IR spectra are formed. Essentially, NMR spectra, you are looking at particular atoms, and the shift is determined by the environment of those atoms. In infrared, you are looking at particular bonds. Anything more than that, rely on your teachers to give you the wording expected by the A-level. So compound Y contains carbon, hydrogen, oxygen, 66.7% by mass carbon. What about the rest? Well, the mass spectrum of Y is shown below. And what you're expected to see is, first of all, peak at 72 that we're going to assume is the M plus peak. Now, if that's true, the molar mass of the compound is 72. 66.7% of that is carbon. So the mass of carbon is 48. Leaves 24. Okay, now we know that there's oxygen in there. One oxygen is 16. Two oxygens are 32. So there must be one oxygen in there, and 24 minus 16 gives us 8 hydrogens. So in other words, we can say that the molecular formula of the compound, 4 carbons, 8 hydrogens, and 1 oxygen. So still with Y, now we're looking at the NMR spectrum. We know the molecular formula of Y, C4H8O. Anytime you got the molecular formula, immediately start thinking, how unsaturated is it? Oxygen doesn't count. 4 carbons usually wants 10 hydrogens, so we're short 2, so we got 1 level of unsaturation. Let's look at our carbon NMR. First thing is we have up there 1 oxygen that's all the way downfield. So it's not going to be an acid because that needs 2 oxygens. So there must be an aldehyde in there that's giving rise to this proton. Okay, and that is, of course, the level of unsaturation. Now we look at what else we've got. We've got total of 8 hydrogens. They're 6 plus 1 plus 1. So each of these numbers doesn't just reflect the relative number of hydrogens, it is the number of hydrogens. So therefore the 6 here must be 2 CH3 groups, and because they're split into a doublet, that means it must be next to 1 hydrogen. Now of course that 1 hydrogen is then going to be split by 6 protons, so giving you a big mess down here for this multiplet. So what can we say then? We know that we've got an aldehyde. We know we then have 3 more carbons, no double bonds or anything. There's the aldehyde. 2 of them are methyl, which leaves 1 carbon left that's bonded to both methyls and has also a hydrogen on it. Right, last question is a nice long one. Solid compound believed to be the herbicide 2,4-dichlorophenoxyethanoic acid. So there we are there, 2,4-D. Following results obtained. Now what we're trying to do is to make sure that everything matches up. So the percent by mass of chlorine present, 32.1. Well, the whole formula, if you add it all up, is C8H6O3Cl2. So it has a molar mass of 221. Percent chlorine is 71 over 221 times 100, which is 32.1%. So that agrees nicely. Solution of the compound reacts with sodium hydrocarbonate, give a colorless gas. That is, of course, a test for an acid group. We have an acid group there. So that agrees. 4.09 grams compound dissolved in suitable solvent, solution made up 250 cubic centimeters, 25 cubic centimeters. This reacted with 24.7 cubic centimeters aqueous sodium hydroxide of concentration 0.750. Well, of course, sodium hydroxide reacts with the acid group. Moles of sodium hydroxide is the volume, 0.0247 cubic decimeters times 0.075 moles per cubic decimeter, which is 0.0018525 moles. Seeing as how we're assuming there's one acid group, that means that the moles of the compound are 0.00185525 moles. Now, that was 0.00185525 moles in 25 cubic centimeters. Okay, but we took 250 cubic centimeters total of the compound, of which we took 1/10 of that. So then the mole of the compound in the 250 cubic centimeters is 10 times as much, 0.018525. And that, of course, was 4.09 grams. So the molar mass of this compound from these data, 4.09 grams divided by the number of moles, which is 221 grams per mole. So this also agrees with this. Of course, this got nothing to do with spectra, but it was there in the middle of the question, so I thought let's leave it in to practice. Okay, blah, blah, blah. Now we're into refluxing with aqueous sodium hydroxide. Did not leave chloride in the resulting mixture. Okay, now, of course, if you take a chloro hydrocarbon and react it up with aqueous sodium hydroxide refluxing, then you substitute OH for the chloride. You leave the chloride floating around. There's, we didn't have that. We don't have aliphatic chlorides. Compound didn't react with aqueous bromine to give either a white precipitate or decolorize the bromine. So that tells us no phenolic groups and no carbon-carbon double bonds. So lots of chemistry, just to give us context. Now the simplified NMR spectrum showed 3 separate peaks in a ratio 1 to 2 to 3. So we know we've got 1, 2, 3, 4, 5, 6 protons on there. Let's look at them and see how they are. We've got 1 proton there, that's the OH. We got 2 protons there for the CH2, and then we have 1, 2, 3 aromatic protons. That agrees with a 1, 2, 3. So assuming that we didn't resolve those 1, 2, 3 aromatic peaks, that agrees. Carbon 13 showed 8 peaks. Well, we got 8 carbons. Are they all different? And absolutely they are. Okay, I mean, you've got this chlorine here and the chlorine there to make each of those carbons in the benzene ring inequivalent. Okay, and then of course this carbon completely unique. So that also agrees. Use all the information to confirm the compound is likely. 2,4-D suggests a simple lab method. Well, we've been agreeing with it all the way through. And how would you confirm? Well, if you know the literature value for its melting point, you measure its melting point, or of course you can just mix a sample with some of the actual stuff and tell the melting point of that mixture and see if the value is unchanged. Kind of a funny one to end up with, but still enables me to have a pretty picture at the end.